Hi everybody. In the first two videos we talked about basics of digital communication and then time domain analysis and frequency domain analysis. In this video we'll talk about ideal sampling, and in the next video we'll talk about Nyquist theorem, which basically applies for low pass signals. So let's jump right into it. So what is ideal sampling? So as we discussed in the first video, sampling is essentially the first step for converting an analog signal into a digital signal. So the input to a sampler is a continuous time domain signal. Say in our example it's x of t, and the output is a series of discrete samples. We call it as x delta. Typically it's represented as x delta of t for a ideal sampling. So how does it look mathematically? So say we take an example where, let's say this plot shows my input signal x of t. So it's a continuous time domain signal. As you can see, it's continuous time domain signal. And the right hand side graph here shows the frequency domain representation of x of t. So in this example, my frequency components span from say minus fx to plus fx. So this type of signal is called low pass signal. So it has frequency components from 0 to some value. It has an upper limit on the frequency component. So we just took an example of a signal that's a low pass signal in our example. So how does the output of sample x del of t looks for in this example? So as you can see here, I take samples at a periodic interval ts. So I take a sample at t equal to 0 here, and then I take an interval at t equal to ts here, at another sample at t equal to 2 ts, another sample at t equal to 3 ts, and so on. And the values essentially are the instantaneous values of x of t. So at t equal to 0, the value is the instantaneous value of x of t. At t equal to ts, again is the instantaneous value of x of t. T equal to 2 ts is again instantaneous value of x of t at that time, and so on. So the output of sampler essentially would look like a series of samples with values equal to the instantaneous values at that time. And usually the sampling is done at periodic intervals. So in our example, I take samples at 0 0 ts, 2 ts, and so on. And of course, mathematically, in 0 is just when I am starting to observe it. So even before that, I have been taking samples. So same thing, I observed at minus t, at minus 2 ts, minus 3 ts, and so on. So this ts is often called as sampling duration or sampling periodicity. And sampling frequency, which says how many samples are generated per second, is 1 by ts, which is inverse of essentially the sampling duration. So that's essentially how sampler works. So just let's define it before we go further. The definition of sampling is the process of measuring the instantaneous values of continuous time signal in a discrete form. So I think as we discussed just now. So let's now see, how do I mathematically represent this output of a sampler block? So this x del of t, how do I mathematically represent? For this, let's first briefly talk about Dirac delta functions. I think all of you know this, but let's briefly do a quick recap of Dirac delta function. So Dirac delta function is essentially a unit impulse function. So for all t not equal to 0, del of t, it's often called as del of t. So del of t is 0 for t not equal to 0, and at t equal to 0, the value is essentially infinity, but the total area under the graph is 1. So minus infinity to infinity, del of t dt is 1. So although so essentially it has an instantaneous value at t equal to 0, and the total area under the graph is 1. Obviously a real signal cannot be instantaneous, but it's just an idealized form of representation for such. So we are assuming the samples is taken at an instant. So this Dirac delta function helps us mathematically represent that. So let's go back up to how do I represent the output of a sampler block. So let me just delete it quickly, my markings here. So let's go back here. So here the left hand side shows my original x of t. So this is nothing but I'm plotting my x-axis is t and y-axis is x of t. So this is how my signal varies over time. The right hand side here shows an impulse stream. So it's a series of impulse, a series of unit impulse or Dirac delta functions at an interval of ts. So I have an impulse at t equal to 0, an impulse at t equal to ts, an impulse at t equal to 2 ts, an impulse at t equal to minus ts, an impulse at t equal to minus 2 ts, and so on. So we all know at impulse at t equal to 0 is represented as del of t, as we all discussed just now. So at impulse at t equal to ts would be represented as del of t minus ts. As we all know, when I subtract independent variable of a function by a constant, the function right shifts by that constant value. So in this case, this will be represented as del of t minus ts. Similarly, at minus ts, this would be del of t plus ts. At 2 ts, the impulse would be mathematically represented as del of t minus 2 ts. Similarly, at minus 2 ts, the impulse would be del of t plus 2 ts, and so on. So when I add all of them, if I want to represent a continuous impulse stream, I need to add all of them up. So it would show up as summation n equal to minus infinity to infinity del of t minus nts. So this is nothing but a continuous impulse stream at periodic interval ts spanning from minus infinity to plus infinity. So I have two functions here, x of t, and I have a function summation n equal to minus infinity del of t minus nts, which is nothing but an impulse stream. So now if I multiply these two functions, I essentially get the output of my sampler. So how do I multiply two functions? When I multiply two functions, at every instant of time, just multiply the value of function 1 and the value of function 2. So since the impulse stream has values zeros, between the time sampling intervals, the value is always 0. So 0 times anything is always 0. So that's why your values are always 0 between these intervals. And at the instance ts, let's say at t equal to 0, my left hand side function 1 is instantaneous value of x of t, and right hand side is del of t. So when I multiply x of t with del of t, it's essentially the instantaneous value of x of t, which is x of 0. So I get an instantaneous value x of 0 here. Similarly, at t equal to ts, I multiply del of t minus ts with an instantaneous value of x of t, and I get the instantaneous value of x of t at t equal to ts. So essentially, when I multiply these two, I get a series of samples of x of t at interval 0, ts, 2 ts, and on the negative side minus ts, minus 2 ts, and so on. So the output of my sampler can be mathematically represented as x del of t equal to x of t multiplied by an impulse stream, which is x of t into n summation n from minus infinity to infinity del of t minus nts. So this is the mathematical representation of output of sampler or ideal sampling. So in the next video we will take it further and we will prove what we call as Nyquist theorem, which essentially defines what is the maximum duration, what is the maximum interval, minimum interval of ts that I can have. So thank you everybody for your time. Thank you.